In this episode, we're going to treat privacy-enhancing technologies, PET, as a toolbox you choose from deliberately, rather than as a single product you buy to magically become compliant. Beginners often hear PET and imagine something futuristic, but the real idea is simpler. These are techniques that reduce privacy risk while still allowing useful processing of data. The catch is that no PET works equally well for every threat, every dataset, and every system design, and using the wrong one can create a false sense of safety. Some PET help limit how much personal information is revealed during analytics, others help keep data encrypted while it is stored or processed, and others help prove something is true without exposing the underlying data. The exam-relevant skill is not memorizing a long list of technologies, but learning how to match the technique to the situation with honest assumptions. By the end, you should be able to explain why matching matters, how to reason from threats to controls, and how PET fit into the broader privacy lifecycle rather than replacing it. A strong starting point is to define what makes a technology a PET in practical terms. A PET is a method that changes how data is collected, shared, processed, or analyzed so that less personal information is exposed or so that exposure is harder to misuse. The purpose is not only secrecy, but also minimizing linkability, limiting inference, and reducing the need to move raw data into many environments. Beginners should understand that a PET is not a substitute for basic privacy principles like minimization and least privilege, because if you collect too much data and share it broadly, even advanced techniques may not save you. Instead, PET work best when they support disciplined design, such as enabling useful analytics without requiring raw individual-level datasets to be widely accessible. Another important idea is that PET often introduce trade-offs, such as reduced accuracy, increased computational cost, or added operational complexity. Those trade-offs are not reasons to avoid PET, but they are reasons to choose carefully and to verify that the benefits are real in your specific context. When you view PET as targeted instruments for targeted risks, you avoid both hype and misuse. That is the mindset you need to choose responsibly. Before selecting any PET, you should start from the threat and the trust boundary, because these define what you are trying to protect and from whom. If the threat is an external attacker stealing a database backup, encryption at rest and strong key management may address much of the risk. If the threat is internal overexposure, where too many analysts can query raw personal records, you may need techniques that reduce identifiability in analytics outputs or that partition data access more effectively. If the threat is untrusted computation, where you want to run processing in an environment you do not fully trust, you may need techniques that keep data protected even during processing or that limit what the environment can learn. Beginners sometimes pick a technology based on trendiness, but PET selection should be driven by the question of which party you are trying to prevent from learning what. Another key factor is the kind of harm, such as identity disclosure, behavioral profiling, membership inference, or manipulation of results, because different PET address different harms. When you state the threat clearly, you can evaluate whether a PET actually changes the risk or whether it only changes the story you tell about the risk. Threat-first thinking keeps the choice honest and defensible. The nature of the data matters just as much as the threat, because some data is inherently more identifying and more sensitive than others. High cardinality data, like precise location traces or fine-grained behavioral logs, tends to create uniqueness that is hard to anonymize reliably. Small datasets, like rare conditions or small community samples, also raise re-identification risk because uniqueness is high even without direct identifiers. Beginners should connect this to the earlier lesson that anonymization and pseudonymization have limits, because PET do not remove the need to consider uniqueness and linkability. Data also differs in how it is used, such as whether it is used for aggregate reporting, individualized decisions, fraud detection, or training models, and those use cases shape what privacy properties you need. For example, aggregate measurement might tolerate some noise, while fraud detection might require precision and timeliness, making some PET less practical. Another factor is the expected recipients, such as internal teams versus external partners, because external sharing typically requires stronger privacy protection. When you evaluate PET, You need to consider whether the data can be transformed without destroying the value that the use case requires. The best PET choice is one that reduces risk while still preserving enough utility to make the project worthwhile. Architecture is the third leg of the matching problem, because how systems are built determines where PET can be applied effectively. In a centralized architecture, data is pulled into one warehouse for analysis, which can make it easier to apply consistent controls, but it also creates a powerful concentration of risk. In a distributed architecture, data stays closer to its source and is processed across services, which can reduce central exposure but can create many pathways where data might leak. Beginners should remember that PET often work best when applied at specific points, such as at data collection, at aggregation time, at query time, or at model output time. Architecture also shapes latency and scale constraints, because some techniques are computationally heavy and may not fit real-time systems. Another architectural factor is trust boundaries, such as whether computation happens in your environment, a partner's environment, or a shared cloud platform, because trust boundaries determine whether you need techniques that protect data during processing. When architecture is considered explicitly, PET become easier to place in the life cycle and easier to evaluate for feasibility. Without architectural awareness, teams can choose an impressive technique and then discover it does not fit the system they actually operate. One of the most widely discussed PET families is differential privacy, DP, which addresses the privacy risk that analysis outputs can reveal information about individuals. The basic idea is that results are modified in a controlled way, often by adding noise, so that it becomes difficult to infer whether any single individual's data was included. Beginners should understand that DP is not about hiding all information. It is about limiting what can be learned about any one person from the output. This makes it particularly relevant for aggregate reporting, analytics dashboards, and statistical releases where many people contribute to the results. The trade-off is that the more privacy you demand, the more noise you may need, which can reduce accuracy, especially for small groups or rare events. DP also requires careful accounting, because repeated queries can gradually leak information if not controlled, and a privacy budget concept is often used to manage that risk. Even at a high level, the key matching insight is that DP fits use cases where approximate aggregated answers are acceptable and where the main threat is inference from outputs, not theft of raw data. When the system needs exact individual-level actions, DP may be less suitable, or it may be applied only to certain reporting layers. Matching DP to the right problem keeps it effective and credible. Another PET category involves computation on protected data, and while the details can get deep, the beginner-friendly concept is that some techniques allow useful processing without revealing raw data to every party involved. Secure multi-party computation, SMPC, is a concept where multiple parties jointly compute a result while keeping their inputs private from each other, which can be useful when organizations want shared insights without fully sharing datasets. Homomorphic encryption, HE, is a concept where computations can be performed on encrypted data and then decrypted to yield the result, which can help when you want to keep data secret even from the environment performing the computation. Trusted execution environments, TEE, are a concept where computation occurs in a hardware-protected enclave that limits what the host system can observe, which can reduce risk in shared infrastructure. Beginners do not need to memorize how these work internally, but they should understand the matching principle. These techniques are most relevant when you cannot fully trust the computing environment or when multiple parties need a combined result without exposing raw inputs. The trade-offs include complexity, performance cost, and operational overhead, which means they should be chosen when the privacy and trust benefits justify the cost. Another key point is that these techniques do not eliminate governance needs, because outputs can still leak information and access must still be controlled. When computation on protected data techniques are matched to trust boundary problems, they can enable collaborations that would otherwise be too risky. A very practical set of PET are those that reduce identifiability through controlled transformation, which includes pseudonymization, tokenization, and careful aggregation. These are often the most deployable PET because they fit within existing architectures and can provide meaningful risk reduction quickly. The matching insight is that these techniques work well when the organization needs linkage for legitimate purposes but wants to reduce exposure in everyday processing. For example, separating identity data from behavioral data and using tokens in most workflows can keep many teams from seeing direct identifiers. The limits, however, are that tokenization can enable tracking if tokens are stable and shared widely, and transformations can be reversed if mapping systems are compromised. This is why these techniques must be paired with strong access controls, auditing, and lifecycle management for the token mapping. Beginners should also remember that these transformations do not defeat inference from rich data, because someone can still learn sensitive traits from behavior patterns even without names. So the matching decision includes asking whether the primary threat is direct identity exposure or inference and profiling. When transformation techniques are selected for the right threat, they provide real value without overclaiming anonymity. Synthetic data is often discussed as a PET because it aims to provide datasets that look realistic enough for testing and analysis without exposing real individuals. The matching insight is that synthetic data can be useful when the need is development and testing, where teams want realistic structure and distribution but do not need actual real-world records. Beginners should understand that synthetic data can reduce privacy risk by avoiding the use of production data in non-production environments, which is a common source of leakage. The honest limit is that synthetic data can still leak information if it is generated in a way that preserves too much detail from the original records, especially if rare patterns are reproduced. This means synthetic data must be evaluated for memorization and for the possibility that a synthetic record might match a real person too closely. Another limit is that synthetic data may not preserve all correlations needed for certain types of analysis, so utility can be reduced. From an architectural view, synthetic data is often applied as a gatekeeper, preventing production data from entering development pipelines, while allowing teams to keep moving quickly. When synthetic data is matched to the problem of safe testing and safe experimentation, it can meaningfully reduce privacy exposure without disrupting delivery. The key is to verify that it is truly synthetic in a safe sense, not just lightly masked real data. Privacy-preserving measurement and tracking and analytics is another area where PET can help, especially when organizations want to understand usage without building intrusive profiles. Techniques like local aggregation, limited identifiers, and output-based privacy controls can reduce how much personal information is collected centrally. Beginners should remember that the privacy risk in analytics often comes from stable identifiers and fine-grained event streams that allow long-term tracking, so PET that reduce linkability can be very effective. This might include approaches that shorten identifier lifetimes, aggregate events before transmission, or limit the ability to query data at the individual level. The matching principle is that these techniques fit when the goal is product improvement and trend understanding rather than individualized targeting. They can also fit regulatory expectations where consent is required for certain tracking behaviors and where privacy-friendly defaults reduce compliance burden. The honest limit is that reducing identifiability can reduce the ability to debug user-specific issues, so systems should provide controlled escalation paths when detailed investigation is necessary. When measurement is redesigned around privacy, you can often preserve most business value while reducing surveillance-like behavior. That is the kind of balance design the exam expects you to recognize. Choosing PET also requires verification because the presence of a technique does not guarantee the promised privacy property, especially when implementation details and data context matter. Verification begins by defining what privacy property you need, such as limiting individual inference, preventing direct re-identification, or preventing the compute environment from learning inputs. It then includes testing whether the technique actually delivers that property in your environment, using realistic assumptions about attackers and auxiliary data. Beginners should understand that verification is a disciplined habit, not a one-time statement, because risk changes when datasets change, when query patterns change, or when systems gain new integrations. Verification also includes confirming that operational controls support the PET, such as access control to sensitive outputs, retention limits, and audit trails. A PET can be undermined if outputs are exported freely or if tokens are leaked into logs and third-party systems. Another verification step is measuring utility, because if the PET makes data unusable, teams may bypass it and revert to risky practices, which creates more harm than the PET prevented. When verification includes both privacy and operational reality, the chosen technique remains sustainable. A common beginner mistake is treating PET as a way to avoid hard governance decisions, such as minimization, retention, and access control. PET are not a replacement for those fundamentals because many privacy failures come from purpose drift, overcollection, and broad internal sharing, none of which are solved by advanced math alone. Another mistake is assuming that because a technique sounds strong, like HE or SMPC, it automatically fits the architecture, even though performance and integration challenges can be substantial. Beginners should also be careful about overclaiming, such as calling a dataset anonymous when it is only pseudonymized, or claiming DP when noise is added in a way that does not provide the promised guarantee. Overclaiming is dangerous because it changes behavior, encouraging broader sharing and longer retention based on a belief that risk is gone. The safer approach is to use precise language about what the technique does, what threats it addresses, and what residual risk remains. Another misconception is that PET are only for external sharing, when in reality internal use can also benefit, because internal overexposure and misuse are common. When misconceptions are corrected, PET become powerful allies rather than marketing terms. As we conclude, the main idea is that choosing PET is about matching the technique to the threat, the data, and the architecture so that privacy improvement is real, measurable, and sustainable. Differential privacy, DP, fits scenarios where inference from outputs is the main risk and approximate aggregate answers are acceptable, while techniques like SMPC, HE, and TEE fit scenarios where computation must occur across trust boundaries without exposing raw inputs. Transformation techniques like tokenization and pseudonymization fit everyday workflows where linkage is needed under control, but identities should not be widely exposed. And synthetic data fits development and testing needs where real records would create unnecessary risk. Privacy-preserving measurement fits analytics needs where trends matter more than individual tracking, reducing linkability while preserving usefulness. Verification and governance are essential because implementation details, query patterns, and data uniqueness can undermine the promised properties if not tested and controlled. PET support privacy best when they reinforce the fundamentals of minimization, least privilege, retention discipline, and accountable disclosure rather than replacing them. When you can reason about PET as deliberate design choices that address specific failure modes, you show the exam-level skill this domain rewards. Engineering privacy into real systems using the right tool for the right job, with honest claims and verifiable protections.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.